Hello everyone, welcome to this stream. Today we will be working on nMigen and learning about it and seeing how to design stuff in the HDL nMigen language. So the main part the main reasoning is why we are working on this today is because Glasgow is pretty much in the steps of being closer to do the next production prototype batch, and Electronic Eel is still working on it. I didn't have a direct thing to work on today, so I was thinking, because we have the Icebreaker Bitsies PCBs already here, and I want to continue working on the Twang game eventually at some point. And because this weekend is theoretically tour camp, so I would be at tour camp now. And I wanted to have Twang actually ready for tour camp, but because of shelter at home, all these kind of things got cancelled, so I was not working on it at all. But I would like to push forward on this project a little bit. And I would like to use, instead of Migen, I would prefer using nMigen to design the hardware for it. And that's why I need to learn a little bit more about it. And you will be witnessing me pretty much learning about it, so we can learn together. So to explain, the Icebreaker Bitsy is an FPGA and Icebreaker as such. So this is the Icebreaker, which is an FPGA development board, and Icebreaker Bitsy is also an FPGA development board. Both use the ICE40 UP5K from Lattice FPGA. And to do things with FPGAs, you need to design some hardware that basically runs or being configured onto the FPGA. Before you can put a soft core, for example, which would be essentially a virtual CPU that is configuring the FPGA to become a microcontroller. And for Twang, the idea was to use a RISC-V microcontroller or a soft core, and then have some peripheral hardware that can send stuff out to a LED strip like this one. So this actual LED strip I bought for that particular purpose. And then we can control it from either a joystick, the game, or I also have some accelerometer, because Twang itself, the game, is using an accelerometer on a spring, on like a doorstop spring, as a controller. So we could read this in, so maybe we need like an I2C or a SPI peripheral for the RISC-V core. So all these things, there's a lot of moving parts. And as you remember, I did the examples for Icebreaker using Litex, which is a system for generating system on chips. And that relies on Migen. So it is using Migen, which is a Python framework for HDL design. But I would prefer using nMigen, which is newer, better, improved, and this is what also Glasgow is using for its applet configuration. So again, tying it into Glasgow, you can design your own hardware for Glasgow that speaks the protocol that you need and codes and then decodes it, and you write that in nMigen to... It's very loud, I can decrease the audio. I was messing around with the music. Let's see, Spotify. Is that better? That should be better. So that's a separate thing. I was trying to add ducking for the music, but I found it too annoying having the audio of the music go up and down all the time. So I stopped doing it. So I removed it again. Anyways, so I hope the audio is better. Now I got distracted. I don't know where I was sitting. Anyways, so we want to be able to, the Glasgow is using nMigen to design the hardware that runs on the FPGA that does the protocol encoding and decoding. So for example, you want to talk with SPI to a device, you generate, it's already written by now, but it's in theory that wouldn't exist for Glasgow. You would write in nMigen a piece of hardware that would be able to decode and encode, so a transceiver for SPI. Then you would have those registers and then sent through the USB interface to your computer. So you don't have to bit bang over USB each pin by itself to implement SPI, but you can have the FPGA do it for you. So that is the tie-in for the Glasgow. And so I was let's see here. So I was looking at this. So this is nMigen. This is the repository. You can find it on GitHub, nMigen. That's the official repository. If you Google for it, you might be getting the outdated, wrong repository still. This is the correct one. This is the most up-to-date, actively worked on repository where White Quark does a lot of the work on it. So this is essentially, so if you are familiar with Python, this should be pretty easy. Even if you don't like Python itself, you have to realize that nMigen itself is more or less using the facilities of Python, but it is not meant to be essentially Python converted to HDL. That is not the goal here. There are some other HDL, so hardware description languages, that are essentially taking Python syntax and converting it to logic. This is not what the nMigen is. nMigen is just embedding itself in Python to use the mechanics of Python so that you can write your HDL within it. It's not, it's a little bit different approach. It could theoretically live outside of Python. It's important to understand the distinction. So if you hate Python, you barely have to use Python itself to be able to use nMigen. You just use this as a underlying machine to use it. So if you have prejudices towards Python, then you should still give it a try and consider it. So the next problem is that nMigen is pretty new and there was not much documentation. White Quark has almost finished the documentation, the technical documentation for it. It's not released yet. It will be released hopefully very soon. But there, as a solution in the meantime, Robert Brauch, he made a series of videos where he implements a 6800 CPU. And as part of this I didn't watch all of it yet. It's on my to-do list. It's like I'm still watching it, but it is a good series of videos. But also, he created a tutorial over here. So it has several steps already, and it's in his GitHub repository. And this is currently the best documentation for nMigen. And so I can recommend this. I did read through this already. It's pretty good. There are some things still missing. I think formal verification is still fairly skeletal. Is that correct? Yeah. So it is not fleshed out, the formal verification stuff. But yeah. Now, why there are several reasons why I will try to explain that in a minute, Grazfather. yeah. So yeah, Ratboy. So yeah, you can use this can target a lot of different boards. So it's like you are not just tied to one. So you can use nMigen with all these chips. So you can use it with ICE40, ECP5, MacXO, MaxXO3, Spartans, 7 series Xilinx, UltraScape, and Intel Quartus stuff. So you don't have to use the open source toolchain backend. Of course, it is the most easy way. It can, no, I think it can actually, it just does generate also Verilog as an option. That's not the default modus operandi. It generates, for example, for Yosys, it generates the Yosys intermediate language immediately. So it doesn't go through the Verilog, which is the advantage of using the direct intermediate language of Yosys is like it is much more specific to what it does. Instead of just hoping that the translation to Verilog and from Verilog does the right thing. So it is, nMigen does more optimization stuff than that. So definitely this process is much more reliable and much more defined or deterministic what will happen at the end. For chips that are not supported by the open tools at the moment, you can always use the alternative tool chains like Vivado, ISE, Quartus, or Diamond. So it is all usable. The idea is, well, it is mainly targeting, of course, the open tools. And the interesting thing, this is today, so few days ago, WhiteQuark announced to have Yosys ported to WebAssembly, and now NextPNR is ported to WebAssembly. That's an announcement from today. And what it does is you are now able to install a package in Python that pulls in Yosys and NextPNR for you. All you need is the database because it's bigger. And basically, we are getting closer to just install the Python package for nMigen and have the complete toolchain platform independent running on your computer. Yes, WebAssembly will be a little bit slower, but it is incredibly portable on all these different platforms, and will make it much easier to just press button and go, and not have to install the toolchain and know how things work. I don't see, for me, it is not a problem. I just install the toolchain, no issue. But for beginners and people that want to get it done right. So Yosys and NextPNR are ported to basically compiled to WebAssembly. So you are compiling Yosys and NextPNR instead of to specific architecture like Windows x86 or Linux, ARM, or whatever. You are compiling it to WebAssembly, and then the WebAssembly engine is running it on whatever architecture it is on. So it is an abstraction layer that you can use. The thing that I didn't understand until recently, it's basically more, yeah. Oh, interesting. Only x86? Ah, okay. Okay, sure. Well, in any case, if you are then on a Raspberry Pi, you still need to install the toolchain yourself. But yeah, so you will be able to at least do the transition between Windows, Linux, and Mac with one binary and be done with it. So binary, well, bytecode, whatever representation. And yeah, so that's pretty exciting, and this will be part of nMigen, and I think this will make work with it easier for a certain group of people. I personally don't see like installing the toolchain as big of a problem, but I'm a different kind of a user. So, the other advantages is like for users of Glasgow. So if you, for example, have Glasgow, you install Glasgow, that has a dependency for nMigen, and nMigen pulls in the WebAssembly tool. So you essentially just install the tool and then pulls in all the dependencies, and you don't need to worry. It's like, what FPGA toolchain do I have to also install to use Glasgow? So it's making it even less of a problem than it was before. So it is just another good step forward. Okay. So where were we? Yeah, that's nMigen. Then there's this this guide, and we can just skim through it maybe really quick. I don't think it is pulling it now in yet. It will have the option of pulling it. It's like, I'm not saying it is doing it now, but the idea is to have essentially a type of a flat pack solution for Glasgow. And if you want to use another route, you might need to install it more manually than otherwise. So that's my assumption, what will happen. But you have to ask White Quark what the details of her plans are. So I'm not exactly sure. The idea is essentially to make it as easy for a normal user to install this stuff, not for you, Sylvain, or me. It's like we are not the people that this stuff is being optimized for. It is optimized for someone who is like, I don't care, I just need this tool to work today, yesterday, in 5 minutes. Well, I'm telling myself the same thing, so okay. Yeah, I think it through pip. Yeah, I don't know. We have to see. I'm sure there will be. We have to optimize things and work on making it so that we have all those options, depending on how we use it. I am 100% sure that knowing how White Quark does things, it will be all flexible, and we will be able to like install it this way or that way, depending on how we want it, so that it is easy to use for that's how to call it in gamer terms. It's like what is it? Casual player versus people that yeah, wasn't time. Yeah, as I say, I'm not exactly sure about the details. I would have to install it myself to like shake out where the issues are and how it works. So don't quote me on it, please. I'm sure it is more complicated and probably more simple than I think, and we will figure it out as we go. Let's not jump to conclusions yet. All right, so let's go really quick through. So what I wanted to do is look into the Icebreaker nMigen examples. We had CR1901 do some commits, and mainly I think Mike Welling CR1901, he did a lot of the examples here, and then Mike Walters, or Meek, he added a bunch of stuff. I only polished a few things. Oh, Alex Hood also committed stuff. So yeah, we have a little bit of examples in nMigen, and I would like to expand this. So I opened it up yesterday and started looking into it. Maybe we should take a quick look at the tutorial and go through the pages first to give everyone a little bit of a understanding. The installation I will ignore because you can go through it as you want. Robert Brauch, he mainly focused on Windows and WSL, which is like it just looks super complicated compared to Linux. It's ridiculous. just installing it on a Linux machine seems like so much easier than what he described here. It's like a lot of caveats and exceptions, and it's like, yeah, you have to take care of this and that and be careful that you don't install GTK Wave with X server and whatnot. It's how can you people live like this? Anyways, so so this is, let's just get to the fun stuff. First of all, we have values or signals or registers. So essentially, the first minor unit in HDL is either a wire where you connect two things together, or you have a constant that is just preset, like a value, or you have a register that you can store things in. And nMigen only differentiates between two, which is a constant value and a wire register. And only depending on how you use that wire register, it defines if it is a wire or a register. So it does that for you. And the interesting thing is you can create a constant, and this carries through all the different primitives. You can create a constant with a value, and then it will automatically determine the shape of it, and the shape is how many bits wide it is, and if it is signed or unsigned. So two's complement, signed, unsigned. And so essentially, if you have a constant with -10, it will automatically determine that it is a signed value and that it is 5 bits wide instead of 4 bits wide, because it needs the 1 additional bit for sign. Same thing, you can say, define, please give me a constant that can carry has a range. So you can essentially force it to be a. There are some questions. Let's see. Oh, you're discussing the Bytecode Alliance, the WASM time. Yeah, I know very little about WebAssembly, unfortunately. Oh, it's ARM Arch 64, so it is not ARM. So yeah, it is supported on ARM, but only on the 64-bit platforms. Is that correct? Okay, no worries, it's fine. You definitely keep discussing stuff, even if it is not directly related to what I'm talking on here. That's totally fine. The WASM stuff is definitely a very interesting development, and it's like I have to learn a lot to understand how it exactly works under it all. 286 Tech, welcome to the stream. Yeah. So yeah, so you can define either if you provide a constant, it automatically will detect how many bits it needs to encode this, and if it needs a sign or not sign, then you can say which range it is to force how many bits wide the object should be, or the constant should be. Then you can also use enums, so you can create an enum and create a const based on that enum. Then it will also detect the size or shape. They're calling it shape of the signal. Then the next thing is signals itself. So signals are more like, instead of a constant, it's more of a variable in programming languages, even though it can be either a flip-flop register that can just save data with a clock externally, or it can be just wires that connect one module or one logic element to another. And you can also decide what shape it should have, and you do it through signed for. This is an interesting thing. So I tried it out on the console. This syntax, this output here, changed just recently, it seems, since this. So this is how fast the development of nMigen is working. So if I go here, let me source the nMigen venv, and then Python from, so that's that. And then if I do a equals signal, let's say signed for, let's just copy what is there. So it immediately shows you, this is how the syntax changed. So the output here, if you have signal and then signed for, it creates this signal with a signed for signal with like 4 bits signal. So it is 5-bit long, oh no, it is 4 bits long, where 3 bits are usable as a value. Oh, Karen, welcome. Oh, right. Thank you, Karen. Can you post it in the Slack for our hackerspace, please, that the stream is running? I forgot. I totally forgot to announce it there. We talked about this. So Karen, or Zebra Girl, she is also streaming recently. She started streaming quite a lot about playing games and stuff, and we wanted to promote in our hackerspace that we do stuff online, and some people do stuff online, so that our hackerspace people can hang out a little bit together. And I promised to post my my content on there, and I forgot. Oh no! Oh no! I'm sorry. You didn't have to. All right. So going back to this, so the interesting thing is it used to show this indication of width, and then if the signed is true, and now it outputs the same things that you can use to input again. So it is much more intuitive. So it is a nice improvement. Cargo rounds are really dangerous. Yeah, that's fun. Yeah, I was hanging out on Karen's streams a little bit. It was fun. So the same thing again, and it continues to just repeat itself. For signals, you can also give it a range, and then it will create the correct bit width signal. You can use enums and create the same signal. So just like with constants, you can do it with signals. And now when I go further, I think there's, so these are values and then modules. Right, let me think. Because there was another thing that was also adjustable the same way, but I'm forgetting. Anyways, so it is fairly intuitive and consistent how you can use things in nMigen. So now we need to group logic together. So we can have certain functionality, just like in Verilog or VHDL. You want to create a module that does a thing, which becomes a black box with inputs and outputs. And so you want to group it together. And modules are a way of doing this, and all you do is create a class in Python that is derived from elaboratable. So you essentially, how you think about this, when you run this Python code that has the nMigen HDL in it, it is being executed, so it describes itself more in detail. It elaborates about itself more so that you can actually create logic out of it. Does that make sense? At least that's the crutch that I'm using for myself to understand how this system works. So essentially you have this Python script that you write, and then you execute that Python script that then talks about this, like generates more of the logic that you can then synthesize and place and route and whatnot, so get the other additional steps. So you can write Python that can modify this HDL logic that you create. So you write in Python things that can, yeah. Am I saying something wrong? Because there's either direction was more. So what did I miss? I missed something. It's weird that they use Python's range. Well, it is. Yeah, I don't know what the problem with Python ranges is. It's like, yes, it is. It is essentially you say it's like which numbers can it accept, like from A to Z. I don't see really this being a problem. It is pretty intuitive for the use in Python. So yeah, I bet that if you think in a certain way, it might be difficult to wrap your head around it, I guess. Non-inclusive right side. Well, right. So that's the yes. So that's the thing that is a Python weirdness where it doesn't include the highest number in the range, right? Because you think about this just like in C and most like programming languages that have a for loop. If you have a for loop, you start at a certain number and then you finish just one number before it. So you write like this is very intuitive to anyone who wrote any C code in their lifetime, where you have a for I equals 0 to I less than a number. So this is the intuitive thing to think about this. It is basically any ranges in Python are implemented that way. So you as if you had a for loop that went to less than a number, and that's where it is. So it is from 0 to n-1. Yes. Even a difference behavior between inclusive, occlusive. Oh God, yeah. Yeah, well, that's why I am trying to jump onto the nMigen thing ASAP and leave Migen behind before I learn it too well and get messed up with the differences. So that's essentially the goal here for me. I don't really want to dig my heels into Migen and just move on to nMigen so that I don't have to think about like learn. Yeah, that's fine. No, the derail is fine. It's like this is why we are streaming, so that you guys can ask questions and we can talk about other details. That's totally fine. Yeah, confusing, or it was done wrong first and then corrected. This is the question. That's always a very difficult question about engineering. Do you stay with the legacy or do you improve things to make it better? And I would hope that yeah, so the exclusive right side, it's very intuitive to anyone who writes C code. It's not so intuitive to anyone who writes something else and or does only logic ever. Yeah, it's more Pythonic. So it is more intuitive if you. So I think in this case, if you are putting this inside of Python already in the first place, making the nMigen side different than Python will really throw you off. So because you are using both at the same time, usually, unless you ignore the Python part and just write Migen mostly. Or nMigen mostly. And I do see a very good reason to make it more Pythonic, because that makes it more intuitive if you are steeped in Python anyways. So yes, I agree. That can throw you off quite easily, and it's annoying for sure. I would argue it should have been done right in the first place, but whenever does that happen? So yeah. All right, so let's get back to it and try to get through the structure. So we talked about constants and we talked about signals, and now we have modules which are have essentially this structure. It is a class that has an init, and it has an elaborate function in it, which then outputs a module. And that module, and you pass it a platform. So the nice thing about nMigen and nMigen, in my opinion, is that it also understands more about the target that you are using. So it has a full machinery to manage pins and its assignments. This is something like, for example, with the icebreaker Bitsy. There was a discussion where Sylvain asked, it's like, can we have the numbers on each pin numbered as the pins of the package of the FPGA itself? This is a requirement based on how Verilog or VHDL handles pin assignments. You have the pin constraints file that takes the physical pin inside the package of the FPGA and then assigns it a name. And if you have a board like this, you can argue it is nice to have that pin number written on each pin. On the other hand, I find it nicer to have the numbers of the pins just in a row, so you can just count through them, and even if you are not looking at them, you know which number is which. And so that just reinforces the numbering order on the board. And in nMigen and nMigen and several other systems, you have an abstraction layer that takes the physical pin numbering and assigns it the device or the board specific pin numbering that you can then attach connectors to. So the platform is the machine that handles that. And I wish there was a way of doing that in pin constraints files for Verilog use, where you can say, it's like, no, I don't really want to deal with the FPGA internal pads. Can I have like an abstraction layer there? It's like just the pins of the icebreaker Bitsy board, please. And now I can assign them according to this. That would be really cool. And I think that would make things easier for use, where you don't have to go into the schematic on different dev boards and figure out which pin is which and whatnot, la la la. So that's my take on this. That's why I wanted to wait to explain that in words. Yeah, but there are some details like where does the numbering start on this thing? So yeah. Anyways, I think the pad pin constraint file thing is the actual problem here that I would prefer to fix than having have to print this on the PCB. But yeah, I hear your argument, and it's like I'm just not really convinced that this is the right approach. That's all. All right, so especially because then it is like super confusing. It's like, what? Which number is it? It's like 22 and 31 and 22 and 11 and 5. It's like, what? So yeah, it is. I would assume that this could be even more confusing to a user. Also, we don't really have space on the top of the board anyway, so you would have to remove it out of the socket and look at the bottom of it before you can do it. And we will have a legend just like we did for this one, and so this should have the correct assignment on here, so you can look it up. So yeah, I hear you, and I'm not 100% convinced. That's all. All right, so we explained what platform is. We will get to that at some point. But yeah, so you Well, I do. I always have this around with my boards, or look it up online, or have it on my desktop as a PDF. It's all these different options. And I'm not pulling this out of the board to look it up. It's like that's not really a thing that I would do. Yeah, so module. Platform, module, we create a module and return the module back. And we then can add logic to the module itself. So this class essentially just generates this class and adds different sync and and submodules to it. So you have essentially like 3 variables here. You have the domains and submodules, which we will talk about next. So domains is where the logic resides. So you have the as a combinatorial domain, which contains only combinatorial logic. So essentially it is clockless, it is always on. You put in, like, change some values and they, in theory, immediately change, which is not true because there's propagation delay. But essentially you put there, you can put logic in there that is just purely combinatoric. And so pure just logic operations chained together. And the second domain is the synchronous domain, which has a clock. And that is where you put anything that needs to happen on clock edges. So you have latch the input into the register and then increment a value every clock cycle and stuff like that. That's what goes into the synchronous logic. And you can use outputs from the combinatorial logic or inputs to feed the data through that are in the synchronous block that happens on every clock cycle. You can create additional clock domains, and so you get additional domains if you have additional clocks. So you would not create more than one combinatorial logic domain. You can create multiple clock domains, and this is one of the things that people I didn't spend enough time doing HDL to confirm or deny it, but at least the claim is that it makes creating designs with multiple clock domains easier. Because it really keeps them apart, and you don't have to think about, like, make sure that you do it right. And then when they converge together, or you have to cross clock domains, you have primitives that you can use, like FIFOs and stuff, that you can plug in between those clock domains. And this, in a nMigen and nMigen, they both make it easier to think about clock domains and their crossover, where in Verilog it is more in one just big giant bucket, and if you are not careful that this module is in this clock domain, this module is in this clock domain, and you have to make sure that you cross it correctly, I think that's at least the claim, that it makes it easier than other HDL languages to actually have multiple clock domains in your design. Yeah, this is like different edges. This is something that I recently tried to do, where I had a sensitivity list on the rising and falling edge, and then Dave Shah basically was like, no, don't do that, because essentially you are increasing your timing requirement by double. Like, you're doubling your timing requirement than your base clock if you are doing sensitivity list. That was in Verilog, if you do a sensitivity list on rising and falling edge. That was interesting. I didn't know that. But yeah, so this is just an example of how you can create a second clock domain. But it's definitely useful when you have, for example, a PLL with 2 clocks outputs, and you want to have like HDMI output on really high clock frequency, but your actual CPU and logic running on a lower frequency block. and then you want to have two clock domains. One is just for the HDMI stuff. This is where the module for HDMI will live, and then you have your CPU living in the second clock domain, and then you have a correct crossover. And it is very easy to read there when you are looking at the implementation. It's like, oh, which one is which and what clock domain what belongs into, because it is assigned directly. Because what you use is you create those domains, and then when you add logic, which will happen later, accessing the domains, ports, as default values for signals. This is not, it's more important when you actually want to write something, but I think there is, next one would be that. Basic operations, yeah. So essentially, if you want to assign stuff or add logic to any of the clock domains, you have this module, domain, combinatorial, and then you add the operation to it. So you have X assign Y plus 1, or in the sync domain, which will be clocked, you can do the same thing, but it will happen on the clock edge instead. And if you add more domains, you can access them under different names than the sync domain. They will just get their additional name. That's at least how I understand it. Correct me if I'm wrong. But yeah, I think so. You essentially can. We will not do this because we don't have to deal with that and create additional clocks. Currently, we have simpler stuff. We just do basic ops, and we will do this. So we will do combinatorial and sync, and we will assign stuff. And then we will be doing probably branching, which this is where things become very interesting. So this is where the split between Python is most apparent to me, is if you write an if and else in Python, this happens at synthesis time. So you execute the script that generates your logic. Whereas if you want an if-else statement in your logic itself, you have to write it this way, which will generate logic that has conditions. So this is where the split between one and the other is the most apparent. You have to think about layers of things. This feels a little bit like the feeling the first time I SSH'd into a server remotely, where you have those layers. You are like, yeah, you are sitting on this computer executing something in the command line, but it is not happening anymore on my computer, but it's happening on the remote computer. This is the type of like layering thinking that is happening. So yeah, so this is a definitive design choice for nMigen and nMigen to keep that separation somewhat clear, so that you are not confused where in the stack are you. I hear that this is different for, I think my HDL is different, where you actually write Python and this is being converted to hardware design. Again, correct me if I'm wrong, take it with a grain of salt. But yeah, here it is, there is certain, like, there's a back and forth where you have Pythonic concepts seeping back into the HDL, whereas also still keeping a separation. This is a very sharp grade to yeah. The good way to think about it is that Python is generating the HDL, and it has to generate both the if and else case, so that if has to execute, yeah. Yeah. Yeah, it wouldn't. Yes. So I think I agree with Gratzfather here. It's like you are so this is living within Python, not the other way around. It is not like Python is a plugin into nMigen. It's nMigen lives within Python. So this choice is pretty clear here, that you write it this way and not the other way around. If you want to write it the other way around, you would write an HDL that uses Python as a scripting language. And it's like, yeah, sure, make that. That's fine. That would be also a decent solution, to actually create an HDL that has Python as its scripting language. But that's the onion wrapped the other way around. And yeah, sure, more power to you. Make that. That's awesome. But this is not how nMigen is built, in my opinion. That would be reverse, essentially. Yeah, I don't see this being like this verbose even writing. It's like if you have so this is something that comes from my short stint of a few years writing Common Lisp. It's like people are essentially obsessed with the idea that the brackets are a problem, and it's so verbose, and you have to write all these things. It's like, get a proper text editor that is actually made for writing Common Lisp, and suddenly it becomes an advantage of having these things. So I think in a lot of these cases, people are just trying to are just writing in a plain text editor code. And it's like, if you have Common Lisp and you have Emacs with the PowerEdit plugin, get PowerEdit and get Slime installed. Both things together are insanely powerful, and you can write, you basically can slurp in constructs, spit out constructs out of the brackets. So a good text editor or a good IDE for a certain language will make writing that language very easy, and even take advantage of the fact that you have those constructs. The same thing I think applies here. If you have a good text editor with good completion and stuff, it should be very easy to write these constructs. Also, having some macros or structural stuff to write nMigen, which will hopefully eventually happen, will make writing nMigen very easy, despite it being more verbose for the HDL part. But now your editor can take advantage of knowing that one thing is that these are two separate things and how to handle them. So I do think it might become, the disadvantage that Sylvain is listing here might become an actual advantage instead of the other way around. It's only if you are writing every single character by hand where these things become actually really tedious. The same argument comes to, it's like, oh, in C you have to call variables A, B, C, D, E, F, G because I have to save typing instead of making it readable. So that is so self-documenting code or like clear code, and it's like, yeah, I do not fully disagree with what Sylvain says there. It's like, it would be nicer to just write the complex stuff first instead, but yeah. Okay. Yeah, I don't know. It's like, I have to probably spend more time writing it, and it's like, I think this is, I'm not sure this is, yeah, I don't know. We will have to see how things shake out. I will have to spend more time writing it before I can make a judgment call if it is actually in a problem or not. So far, I found it similarly, like no more or less trouble than reading Verilog so far, especially because this looks immediately different. It was clear, oh, this is logic, so I have to, yeah, you only see the highlighted stuff. It's like switch, case, default. Oh, okay. Everything else just disappears. It's this, again, let me go back to the Common Lisp analogy. The parents disappear. With a good pretty printer, the parents disappear. This is a similar thing. With a good syntax highlighter, the fluff disappears, and so reading the logic here will become pretty obvious. So I don't know. I think it might be actually yeah. Rainbow Parents ++, yes. I don't know. I actually didn't use that. I preferred the indentation of the pretty printer and the sorry, super tangent, but yeah, the pretty printer in Common Lisp, it actually takes makes sure that the indentation, how much it is indented, is very structural. So it's not always the same indentation if you do it right. So depending on what type of structure you have, the indentation changes to make it visually visible where you are in the structure of the code. It's a very interesting thing, and when the pretty printer starts screwing up it's really hard to read. Because you are confused. It's like, wait, why is this indentation off? So yeah, that's complete tangent there. Okay, so this is how we have switch cases and then if statements for bit patterns. That's an interesting one because we will see that in a minute. If we have an if statement which we want to match to a bit pattern, we can have those wildcards where these bits, for example, don't matter. So you can match stuff with ignoring bits, which is pretty neat. What else? Then that was branching. Then the next one is combining. So we can combine multiple signals together. So we can address stuff within a signal with the array patterns. We can even have step. Somewhere is an example for that in here. Yeah, where was that? It was in a different. So this is the Python thing that I didn't know that I needed until recently. Oh, there it is, the stride. I didn't even realize that I wanted this. So you have from 0 to 8, but with a step of 2. So every second bit from 0 to 8. When I learned about. Welcome, Jordy. Don't worry. I know you have better things to do. Welcome to the stream. Jordy. Look what arrived. Yeah, there you go. You can rewatch it later. We will be assembling them very soon. All right, so I didn't even realize that I wanted this, but it is actually pretty useful in Python. And then also assigning stuff to the selected signal. So of course, :8 means from 0 to 8. Or -1 is the last bit of an array and stuff like that. So it's just standard Python array access for the different bits and groups of bits inside a signal, or whatever, or a const or whatever. Then this is where we have operations. So if we want to assign to a single signal yeah, so what was it? Expect when overflows. Oh yeah, you have to be very careful with overflows. This is a thing that we might run into eventually. This is where the Pythonic thing of automatically adjusting the bit width based on what your content is might become an issue. So this is where Sylvain's argument about it's like, I hated how Pythonic it is. It's like, well, yeah, that is something I find that might be more of an issue than anything else, where Python always, all the variables can be as much size as they need to accommodate the value, even if it has to be a synthetic value content. And this does it here too. So you are not pre-declaring. Oh, Timon, welcome. Welcome to the stream. Nice to have you here. So we can add, so if you have two values that you want to add together, it will expand by one bit when it is a big value. So you have to force it to be a smaller value. It won't, in Verilog, it wouldn't do that. It's like if the variable that you're assigning it to is smaller than the input, then it will just trim it to the input. Here so I don't know where the bigger problem is. It's like that you can assign a too big value to a smaller value and not get an error, or even though I think Yosys does say if it is trimming values. So it's really difficult to say. It's like, should it happen before compile, like synthesis time, or after synthesis time? Should it be a warning? Should it be an error? Where do you put it on the scale of severity of the issue? This is probably a discussion to be had and decide which like approach to take. I think this is all this stuff, like having more HDLs emerge and having something beyond Verilog and VHDL come out, has the advantage that we can have those discussions, what is better, what is worse, and where the pain points are. And that is an interesting one that we probably should also discuss. I'm sure there are much smarter people that already discussed it, and I I shouldn't be the person here. But yeah, so that's a thing you have to take care of. You can also concatenate signals. So basically you have like a bit and you want to concatenate it together from different sources together. And for that you use this cat function. Robert goes into more detail in here. Then we can have also arrays of signals to group things together. Layouts. What are layouts? Oh, these are like predefined structures that you can use. It's like, I don't think we will be getting into this, definitely not today. Connection records, buses. So you can have buses to connect things together. Yeah, this is I think beyond what we need, at least for now. What I like about nMigen and nMigen is the built-in simulation stuff. So it is not like living to the side of things. So this is, yeah, I don't know how nMigen does the buses stuff. It might be an nMigen only thing. So yeah, so we will definitely use all of this stuff eventually, but you should probably just read this tutorial by yourself to learn about the details at your own pace. But yeah, I'm just trying to give a slight overview over these things. Then simulation. So that is an interesting thing. So what I like about this, it is living within the same Python file, and you can essentially just have the simulation next to it, next to your actual executable code. This is pretty neat, in my opinion, how it integrates the simulation with the synthesis all together. There is an example we have already in the icebreaker and nMigen examples that we will get to play with that, and I will show you how nice that is. Yeah, so there are some details about how to set it up, and it is essentially using generators or generator functions to do the simulation. So with each yield, you have one clock cycle of the simulator go through, and so you can yield multiple times to advance the clock, and you can even go from running mode into a passive mode, which is like a little bit of a detail there, where you basically have the generator function only set up things for your logic, and then you let it free run without where the process basically says, oh, I'm done setting up things, and you run however long you want, and you only set it here when you execute it here. Run until you say how many clock cycles it should run. So the process doesn't have to cover the complete scope of this time frame. It can basically excuse itself and leave the room while the simulator continues the simulation of the logic, which I found very interesting. So yeah, that is the processes. Because the important thing here is if you just select the run until and the process finishes, the simulation will also finish without reaching the time point that you listed here. You have to go into passive mode, which you do with yield passive, I think. Settle, delay, wait, where is it? There's like somewhere in here, there is like switching to passive. Run until, oh yeah, run passive, wait. There it is. Yield active, yield passive. That's what I was looking for. So you yield passive and you say that your process is now passive. And then with run passive true, this will run for the 100 to 10 minus 6 clock cycles. And then finish instead of just breaking off early, which is pretty neat. What a big, in my opinion, and huge advantage of nMigen over nMigen is nMigen also got formal verification. So what that does, you can essentially set up assertions of what your logic should look like at certain stages of your execution. And then when you run the formal verification or symbiosis on this, it will try to find a way to disprove your claim. So essentially, it is you are asserting at certain things and saying it's like, this is what it should be at a certain point. And symbiosis will do its magic to really quickly show you it's like, no, you're wrong, your assertion is wrong, and here is how you reach the thing that disproves your claim. It's freaky. It's really freaky. I didn't install Symbiosis yet, so we can't try it out today, but on a future stream we will definitely try it out. I think Robert shows it on his second video, Symbiosis, so I definitely recommend that you watch the second episode of his series about 6800. That is very, very exciting. I'm really looking forward to play with this and do asserts and covers and whatnot. It's still mind-bending to me, but that is something that is very, very exciting to play with. Oh yeah, Matt Vance formal class. Yeah, I have to check it out too. He did something there. That's a good question. You will have to ask Matt. Or I think it was a tryout class that you could apply to, and it was like on a video call, like a webcast or something. I'm not sure if he published it for everyone to access. I would hope so. But yeah, yes, it was a beta test on Zoom. Okay, cool. Yeah, the question is, can we watch it or not? Yeah, I don't know. I don't have the answer for that. But yeah, the alternative, there is ZipCPU's website, which has a lot of stuff regarding formal verification. What did I do here? ZipCPU blog. Formal verification, there it is. So I think he has a lot of blog posts regarding formal verification on his forum. Yeah, there's a lot of stuff here. I still have a lot to learn regarding formal, but yeah, that's the place that most people recommend, because ZipCPU spent a lot of time describing it and making exercises and tutorials and whatnot for formal verification. Okie dokes. So yeah. Anyways, that would be this really quick intro to nMigen. I will take a very short break and we can look at the examples that we currently have in Icebreaker, and maybe we can do something porting one of the Verilog examples to nMigen, maybe. So let's try doing that. But I need a short break and I'll be right back. Alrighty, I'm back. Sorry about that. Anything I missed? Right. So, right, but you don't understand what that means? You mean porting Verilog to nMigen? So, if we look here, we have soldering without you. Yeah, did you solder some of the icebreaker bitsies already? Or are you slacking off? Yeah. So if you look at the icebreaker FPGA organization, we have a bunch of different repositories here. Yeah, we are working on the website, so or Jordi was working a little bit on the website. But yeah, oh, that's another thing. It's like I'm moving the domains around. Did them all. Okay, okay. Oh, very good. Yeah, so we have a bunch of collections here. So I should make it more clear that the Icebreaker workshop is the more up-to-date version, and you should be doing this workshop because people gravitate to the WTFPGA. I should probably update it and link to the Icebreaker workshop a little bit more clearly. But yeah, it's not what we are here for today. So Icebreaker examples, there are multiple different platforms. We have the iStudio, we have nMigen examples, we have examples per se, which are just the Verilog. This is written all in Verilog. And these are the examples that we currently have for the Icebreaker. So this is Verilog. And we would want to port one of them maybe to nMigen. But before we do that, let me show you what this looks like. These are some examples that are written. Yeah, there we go. Yeah, some Icebreaker examples to nMigen that are written in Verilog to nMigen. So here are the examples we currently have for nMigen. So this is how simple this actually is. There's not even comments in here, but essentially all you need to create a working code is you have to load the platform, which is the Icebreaker platform. Then you need Blinker, which is the module that you want. So you have a module here. And this module then asks the platform. So out of platform, we request the clock 12. So this is the interesting thing. Let's see, can I show you a platform definition file? I think that might be useful to have. How do I do it this stupidest way? Oh, share the screen? Yes, thank you. I'm sorry. There we go. Okay, let's go back. Okay, thank you. I need like some announcement horn or something. Oh God, yeah, sorry. So these are the nMigen examples. I think we even started earlier than here. So this is the Icebreaker FPGA organization. We have a lot of repositories in here. We have nMigen examples, Icebreaker hardware design. These are the Verilog examples here. This is the Icebreaker PMOD designs. Then Litex examples, which is just SoC or RISC-V SoC stuff. Then we have workshops that you can use to learn about like basics of FPGA design. And then there are some cases, mechanical cases for the Icebreaker. So we have a lot of stuff in here. And all we will be doing is trying to port one of the Icebreaker examples, one of these guys here, to the actual nMigen stuff. I hope we can find something simple enough that it will be possible to keep in this scope. So this is how an nMigen design that just blinks an LED looks like. We have the platform, which is the icebreaker platform that we load. So from nMigen boards, we import all of them, and then we just instantiate this one platform. And I wanted to see if I can, let's see, this is just used in the open files. I don't think I can just directly jump to it. I think this is just nMigen. nMigen dash boards, I think. Yes. So in here we have, for example, the icebreaker. There it is. So that would be a platform file. So icebreaker platform, and this is what I was talking about having definitions. You have the resources that you can instantiate and describe in more detail than just a pin constraint file. So that's what I really like. You have what device it is, what package it comes in, what the default clock is of that design so that it automatically can pick it up, and then describe the resources, have LEDs and what actual package pins. This is what Sylvain was talking about. It's like having the package pins for the FPGA, which they correspond to naming and what attributes you want to have assigned to them. I'm not exactly sure what the star means in here, because that's a different thing in nMigen, I think. They're like optional or something? Yeah, I don't know. That's something I will have to learn about. Button resources, pins, 10. Invert true. Oh, so this is like a set of resources that basically refers to a more than one pin, I guess. So these are groups. These are bigger groups, I think, maybe. Yeah. And then you have a connector which you can then essentially plug in things into, like logically. So you have the connectors, the 3 PMODs, which say which pins they are, and you can even have the spaces to indicate that these pins are not accessible on this connector, because this is power and ground on those PMODs. And then we have a break-off PMOD, which is the actual device that you can add. You can basically go in your module and plug that in and say it's like expand, and then plugs this in, and then all these names become available for you. So you suddenly can access all these pins with their names, instead of, again, having to figure out which pin of the FPGA it actually is and what direction the pins have, and. So it makes it incredibly powerful, and you can create those in your designs themselves, saying it's like, oh, I have this thing attached to this connector, so this is what I'm actually talking about. For example, HDMI PMOD or HyperRAM PMOD. These can be all these expansion things that you can just attach to your design. Next. So toolchain program is what toolchain is being used to synthesize your binaries. This is something for the platform too. And oh yeah, see, add resources. So you can have additional resources here. So you add this resource to this design. All right, so now that we know how a platform looks like, we can go back. Let me, let's go back here. And all it does, it takes this module, which would be this elaborate. We have a clock, we have an LED, so we request LED R and we request clock 12. We create a module, we assign to the sync domain that this a clock domain, and that clock domain should be equal to, so in the combinatorial domain, we assign to this clock signal, wait a second, clock domain, domain sync. Oh, it does it automatically, I guess, because I don't see clock signal. It has to happen somewhat automatically, this relationship between these two. So, okay, there's a little bit of magic happening under the hood here, because clock 12 just equals clock signal, and clock domain is also like assigned magically, and it suddenly happens. So yeah, there's some magic happening underneath here. It's quite flexible compared to just typical pin constraints. That's true. Okay, so let's look over this. So I'm not 100% sure how this works here, and that is, I am a little bit confused. But yeah, it has to do some magic in the background. Okay, so then we create two signals. One signal is a counter, and it has a range of max period +1. So that's what Sylvain was complaining about, that we have to do the +1 here instead of just saying max period. So max period is n-1, so we have to add the 1 here. Then the period is, that's interesting, period, max period, counter, period, combinatorial, period equals max period. Right, so this could be a const, right? That's why I'm looking at this skeptically. So this could be const and just have the max period as this, unless we assign to period anything else. Yeah, we don't. So this could be a const. We can try that out after we try this out. So max period, yeah, this is at synthesis time. We create this blinker with the max period. Yeah, so I think we could make it const here and then say what the range should be so that it has the right bit size. And then we don't need this stuff here because this is assigned permanently in the combinatorial to this constant. So it would collapse these two lines into one, I think. Then we have if counter is equal 0, then the LED should be equal to not LED. So we should flip the LED. And the counter should be equal the maximum period time, right? And otherwise, it should be just the counter being incremented. So every time this is happening in the sync domain. So every time the counter is 0, this in the sync domain we are flipping the LED and resetting the counter. Otherwise, we are just incrementing the counter. And then we return the module, and that's it. So now we can run this. Yes, so this is how you add additional logic to, you have to think about this. We are adding additional logic to the sync domain. That's why plus equals. So, we like if, and this with if essentially wraps that logic with the if statement. So that's why it is this with construct. So this is wrapped with the if and assigned to the sync domain, and this is wrapped with the else and also added to the sync domain. I don't think it is. I assume that the person that wrote this originally maybe didn't know about const versus signal, and they just used the signal as a const, which that's my assumption. There was no documentation, like completely no documentation back then when that was written. So I would assume that it might not have existed back then. Yes, nothing changes the period at all. That's why I'm saying we probably can collapse it to a const. Nor a signal. Pretty sure max period is not a const nor a signal. Yeah, you have to, I think max period is just a Python variable, and you have to convert it to an HDL constant, I think. I don't think you can just assign, well, no, maybe we can. Let's try everything. That's what we are here for. Just wait. So first of all, let's just where is it? Come on. Where are my terminals? No and no. So this is this terminal. Where am I? Well, I'm now lost a little bit. Oh yeah. So I have to go icebreaker, icebreaker examples. No, nMigen examples. And then blink, then Python, blink py. And I have to connect the icebreaker to this. So this is the icebreaker and it's connected. Maybe we can even zoom in so that you see when that happens. There we go. And focus. Perfect. Now let's do this. And yes, export. Let's try it again. My toolchain was not in the path, that's why. There we go. All synthesized and blinking. So the red LED should be blinking. I hope this is visible. Yeah, so let's see. I have to, how do I adjust this again? Plus minus here, I think. Yeah. There we go. That's better. Is that visible now? Okay, cool. Red LED should be blinking. Okay, cool. So it built and synthesized. Now we can try a few things. So first of all, the recommendation was to actually make it into a const. That was my first thought. So if I do just this, const, and then yeah, I don't need to do this. Yeah, let's try just do this. Max period. Yeah, and there's even a constant literal integer value. Value integer shape. You can have the shape and then number of bits. You can, so you can call it like comma unsigned, and then how many bits you can have it in here. But let's try this. Did I save it properly? I think I did. Let's try it again. Okay, cool. So it seems to be working. Yeah, -1, yeah. So max period to have it assigned there. The alternative was someone was saying maybe we should try this. Can we do this? Just directly have self max period in here. Maybe simplify self.max period -1. Yeah, but let's try this first. Yeah, that's totally usable. You can just directly use the constant from Python in here. I think. I am slightly confused by the fact that I don't have a visual indication that it resynthesized stuff. It's like it doesn't say. It's like, oh, I ran Yosis and next PNR here for you. That's what I'm confused with. Yeah, I wish. Is there like a verbose thing? No, there's not even a help. I wish there was a more verbose mode where it says that it ran Yosis and synth. Yeah, I think it is default clock. Yeah, I think this shouldn't be necessary either. This and this shouldn't be necessary. Let's try it again. Okay, I have to break something now to make sure that it is actually doing anything, because I have the feeling that it's like we are just keep. Yeah, okay, so I am changing the file because things just keep working. Okay, so this is definitely a cleaner solution here. The counter is the one that I am. Yeah, so yeah, I do have to. Let's see. There should be a better way of doing this, because this +1, I do agree with Sylvain that this is annoying in a way, but it is the logical thing for Python. Yeah, I have to agree that this is weird. So yeah, let's do this. Let's make it cleaner and leaner. Clean, mean machine. So like this. Anything else? FPGA toolchain repo replacement for summon FPGA tools. No MLs. Clean again. To clean again, counter -1 may be used before MF default behavior. Default behavior. Oh, you mean this will override? So you mean if I just do this md sync and then essentially have this and only the if afterwards, this will be equivalent? That's interesting. Also, we don't need the brackets here. Like this. And then we don't need this. Oh God, I keep forgetting what the combination here is. Whatever. Like this. Outside of the with block. So you mean this, it will still, yeah, well, let's try it. It's fine. It's like, let's just try it. Yeah, it does synthesize. And it seems to be working. Oh, the brackets are not necessary. I'm not combining more than one statement at a time. So you need the brackets only if you do more than one statement. So here are two statements. There's the LED equal and the counter equal. Yeah, this is why I don't need the brackets here. It has nothing to do with the with block. I could have the with block and have twice the MD sync LED and then MD sync counter to write the same thing. So yeah. But to be fair, if I leave this outside here, it is cleaner in a way, but it is not as readable. So I think I do prefer leaving it in the else statement. So that it is clear when it happens, because this happens all the time unless it is overridden by this, which is fine if you know this, but I think it is easier to read with the if-else statement. That's my take on this. So I will actually revert this. But I will remove the brackets and do it like this. I think that is better readable. I'm trying to parse what Jordi GW is saying there. Yeah, some magic. Yeah, so yeah, the main confusion I think that comes from this is like, because you are living within Python and then you are writing this other code in here too, that is the HDL. It's like you have to like keep that mental barrier between Python code and the HDL code and like which part belongs to what. So knowing enough Python here is probably useful to keep that barrier. So let's see, that should synthesize. I think this is better readable this way, and it doesn't have so much fluff. That's why I was like confused about why this stuff was in here. Anyway, so I think that's pretty good, and we see that this works. So we can move on to the next one. I think the 7-segment counter is the next example that we have in here. It's a little bit bigger, and that one consists of more than one module. So we again have the Icebreaker platform, and we add the resource of the 7-segment PMOD. So 7-segment PMOD is defined. So this is this guy. Where do I have it? So this is a 7-segment display PMOD. And we plug it in here. And we also plug it in our design. So add resources 7-segment PMOD. And it is defined on the top of here. So let me go there really quick. That's the 7-segment PMOD. And this is the overall name. And then it has all the pins. So this is anode A, anode B of the A, B, C, D, E, F, G segments of the 7-segment display, and then the cathode A, which is basically switches between one and the other digit. So when it is low, it is one digit. When it is high, it is the other digit. So it can flip between these two digits back and forth. And after adding this, we also have the top, which is the top design module. And that is here. And in Elaborate, we have again, for no reason, this stuff here. 7-segment pins. That makes sense. We get the 7-segment display pins out of platform that we plugged in right before it. Yeah, this is something we will remove later, but yeah, that will be the cleanup here. Then we have the module, again, clock domain sync. This is something we can remove. Then we have a 7-pins cat. That's the cathode. Signal 7. Let me think. Oh yeah. So this is 7 pins for the different cathodes. Then we have a counter, which is a 30-bit long signal. Then we have a ones counter, which is 4 pins. Then tens counter, which is another 4 bits. Display state, this is a state machine that we run through. So essentially we have a state machine in here that will do different things on different clocks. So let's get to that. So we have a converter that converts, we have a submodule here, which is initialized here in the init function. So digits to segments is a class. So this is a module that we use, which is converting a binary number between 0 and 10 and converts it to a digit code to display it on the LED panel. But because we cannot light up both digits at the same time, we have to display the tens for a period of time and then the ones for a period of time, and flip back and forth really quickly so that it seems that they are both on. And thus we have 2 decoders, and these decoders are combinatorial. So this is the switch. So you have digit, which is the input, so 4 bits input, and segments is a 7-bit output. And then we have a switch statement, so which uses Python to generate a case. So you see, this is the combination between Python and the nMigen part. So this is nMigen, and this is Python. So for n in segment value, n segment value, we have an enumerate of this. So we have these codes, which is all segments on besides the highest level on. Array is maybe better. It's possible. So essentially we just count through this. The reason, I think the reason here is so that we have the ends, so that you have the number and the decoder value. So we essentially have case 0, that would be 0. So that displays a 0 number. So this is the middle. Maybe I can show you how the segments. Yes, that's why enumerate is better choice here, because you have the indexes. You need the indexes. So you are trying to convert I think I have it. Yeah, there we go. So you see that's A, B, C, D, E, F, G. So bit, this is the highest significant bit. We go from right to left. So this is the least significant bit. 0, 1, 2, 3, 4, 5, 6. So 7 bits. Well, if you iterate through an, so this is a Python thing. So if you iterate through an array, you don't get an index. You have to generate your own index. With this enumerate, you get an index and the value. So if I just made a for segval and just have this array of different decodings, I would only have the decodings and not have the index, and I would have to count the index myself. That's why. And I need the index because the digit, which is the input, comes in as a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 7, 9, right? And I need to decode that into a segment pattern, which that's why I have a switch digit, case, n, from 0 to 9, and then I have the 7th segment, which is assigned to the segment's output. Does that make sense? I hope that makes sense. And so we start with a 0, which would be all these segments besides the highest significant bit being lit up. So we have 1s and a 0. And then 1 would be just BC, so second, third. And 2 would be A, B, G, E, D, and so on. So these are the patterns for the different segments lit up. So we create the cases. So we add the cases using Python iteration over an enumerate, because the enumerate gives us the number where we are and the segment value. So that's why enumerate is the cleaner choice here. Also, what is interesting, this is in the sync domain, so we should keep in mind that this is also clocked from the clock. So we are not feeding clock through here, it automatically does it in the backend, running the clock to each of the sync domain stuff. So that's pretty cool. So we have 2 of these which run in parallel for the 10s and the 1s. That's important to keep in mind. And then we have those in the submodules. We assign them. So we have to basically instantiate them. So we have nMigen array. I see. Okay, that makes more sense. So basically to have just a lookup table with an array. That would be an alternative, yes. That would be a solution. I just don't exactly know how arrays currently work. I think you could have just a combinatorial thing, like in a COM, to essentially just have a lookup table. That's a very good recommendation here. Instead of having here a switch statement, have an array. But the question is, aren't they both equivalent at the end? Yeah. So yeah, that's where the things become tricky, where you're talking about creating an array in Python to generate a case statement with all the elements versus using an HDL, aka nMigen array to look up things. So yeah, tricky. Yeah, I will have to look up the array. We might be able to make it different. This would be an alternative implementation. At the end, it might work the same. I don't know. So let's. So this is the important part. If you have a module that you instantiated, just assigning it here is not enough. You have to tell nMigen that you actually want it to be a submodule. So you assign it to submodules. You can choose whatever variable name it is. This is the magic here. All these variables are automatic. It's like it's using syntax tree traversal to actually extract all these by itself, so you can name them yourself. And this is another thing I learned when I was digging through LaTeX. When I was working on LaTeX and seeing how the documentation is being generated, it essentially just, so what are all my local variables and what are their names? Please tell me. And the introspection that Python has for this kind of stuff is just awesome to automate things like this and actually name them correctly. So you can choose any arbitrary name here for a submodule and it will retain it. Okay, so we have those two. And then we have another combinatorial block which takes multiple things. So it does a bunch of different things here in a group. So it combines all the segment pins, A, AB, AC, AD, AE, and so on, and assigns to them, so you combine them on the left side here, which is interesting. So you can combine them on the left side and then assign the 7 segment cathodes. And this is this signal here. So 7 segment pins cathode. And that one comes out later. We will see how this is being assigned later here. Then ones counter is equal counter, these bits of the counter. Tens counter is the higher bits of the counter. Again, we slice it and dice it and assign it. This is so we don't need cons or anything. We can just access it. Then we have display state, and that uses the lower bit. So we have this big counter, and we use the lowest few bits to rotate really quickly through to go through different states of the state machine. The next few bits is the tens counter, and ones counter, and the even higher bits are the tens counter. And we could go on with more bits. So we slice 4 bits out of here, 4 bits out of there. And yeah, so this is the counter. And then we have digit wants to segment. So we take the module, take the digit, and assign it the ones counter. So this is where we plug in our counter output from here into the module. So the module that we looked at that is doing the decoding is now getting its pins plugged in. So we plug them in and plug them in again here for the tens counter. So now it is all hooked up in combinatorial logic, so it is permanently connected. And then we have in the sync domain, we have just the counter, just like we decided not to do in the previous. In the previous example, we can have just the counter to be incremented at every clock cycle. So that's what we want here. This is the counter that is free running and keeps running higher. Here now we have the switch. This is the state machine that we basically just run off the lower 3 bits of the counter. If the bits are 0, 0, 0, or 1, we assign it the 1 segment. So for 2 clock cycles, the cathode pins have assigned a I see. Okay, I was just trying to parse more down here. So these are the cathodes. You also see there's the anode, the selection of which digit it is, so that we know if we are higher or lower. So this one is 0 and 1, and we'll flip beat back and forth. So we do assign these pins, then we assign a 0 to switch off so we don't get any ghosting. We switch it off for 1 clock cycle. Then with another clock cycle, we flip it to the next digit. And then with the next clock cycle, for 2 clock cycles, we will have the tens digit displayed. Then we switch it off again and flip back. So we have this sequence of actions that we go through based on the clock. We have first clock, we display tens. Second clock, we display tens. Third clock, we switch it off. Fourth clock, we switch to the next digit. Fifth clock, we display the tens. 6 o'clock, we display the tens, then we again switch it off, we flip back and continue. So we continuously rotate and flip back and forth, back and forth, back and forth between the two. And that's it. That's essentially all it does. I hope this was not too convoluted and I didn't confuse you more than I explained. But essentially, that's what it does. And now we can run it. No, not make proc. And there we go. There's the counter. So it is counting. Oh, right. It goes further. This is not just tens. This is a complete hexadecimal counter. Correct. So it goes to A, B, C, D, E, F. So that's why it is 4 bits. It's not so it is not actually not ones and tens. It's ones and sixteenths. So this is a 16 digit, right? Or 8? No, 8. What am I talking about? So this is ones and this is 8. Or what? No, I'm confused. Yeah, I know we need even for a decimal counter, but this is a hexadecimal. So yeah, they are both 4 bits. That's correct. Oh God, now I'm confusing myself. Oh man, it's yeah, I'm already mush. It's yeah, my head is mush. We are already at 2 hours. Wow. Yeah, anyway, so I think we went through a bunch of the nMigen stuff. Let me show you one more thing with this. So we ended up actually talking more about existing stuff than anything. So there is a gamma PDM. So this is an interesting example. It's much more complex. You should, yeah, with the clocks. Let me clean this up while we were already at this. So I don't think we need this. And I don't think we need this. Right? Yeah, so that's better. Yeah, we could try the array thing here, but I will leave it for now as it is. Let's try it. Yep. I did save it, right? Hope I did. Let's run it again. Yep, seems good. Oh, Rataboy, thank you for your subscription on Twitch Prime. I really appreciate it. Thank you so much. Yeah, somehow the notifications today are not something I see. Let me just send a test really quick here. Yeah, I don't hear them. That's the problem. Yeah, I completely don't hear them. Something is broken in my setup, so I don't hear notifications. That was just just a test. Yeah. Anyway, so sorry if I missed you following the stream, and I missed you, but I appreciate it nonetheless. All right. So now that this is clear, we can do the same thing for. At least I caught you, Rataboy. Ratboy, right? Yeah, it's a lot of people that watch these streams are not really Twitch people, at least not yet. So yeah, for me it was also quite a learning curve. So don't worry, I feel you. Okay, so let's see. Why is it complaining? Expected 2 lines of blank space before. Right. Yeah, I'm curious if that's all that it needs. Yeah, I think that's all it needs. Stop complaining. There are multiple things that I should clean up here in the gamma PDM from the style, for the style points. But anyways, so this thing is pretty cool. So what it implements is a well, it's an LED fade. And to fade LEDs, you either can do something that is very typical for microcontrollers and have a PWM generator, which means you have a counter, and for a certain period of time, so you for a certain period of time you switch on the LED and then you switch it off again at a very high speed, and the ratio of the on time versus the off time creates an effect of being dimmer or brighter. This is basically fooling our eye to think that there is like actually a value change, even though it is just our eye averaging out how much light hits the retina. And with PWM is the normal thing that you would do on a microcontroller, because you can reuse it for many different things, and it is very, very reusable for different things. On an FPGA, we can do something one better, especially when you just have one LED or two LEDs. Instead of switching on the LED for a period of time, counting, and then switching it off, so you have a counter and a comparator, and if the comparator is, let's say, half of the value, it will be on for half a time and off for half a time. You can have PDMs, which is pulse density modulation. And it means it continuously aggregates an error when it switches on the LED and off the LED. So with each cycle of the clock, it calculates how far off from the desired brightness value are we at. And so the advantage of that is if the brightness, let's say, is 50% brightness, the LED will blink with the full clock speed on and off constantly. So it will be on, off, on, off, on, off. So it has a very high frequency at half value. Same thing when you decrease the brightness value, you basically maximize the blinking frequency based on the brightness you are displaying. So it is like an adaptive frequency thing. So essentially, if you have 2/3 of the brightness, let's say you want, then you will have it on for 2 cycles and off for 1 cycle. On for 2 cycles, off for 1 cycle. Or you have 1/3. So you have at full clock speed just only 2 cycles on and 1 cycle off, instead of being for many cycles on for 2/3 of those cycles and then off, which will create like a bigger time chunk frequency. So that's PDM to explain, and this implements PDM. And we have the cool thing about this example is that it actually also comes with a simulation run. So if you just run it, and let me just run this example. Also, it is gamma compensated with a lookup table, I think. So this is has a gamma level converter. Let's see. Yeah, you have memory here. So you have memory, which is has a gamma table stored in it. So you can also, the gamma table generation is written in Python. It populates a memory block in the HDL from Python. So you don't need a separate tool or separate software to generate the gamma table to load into your memory. I think you could do it in Verilog, like writing some macro that populates the gamma table within Verilog, but I'm not sure how tedious and annoying that is. But probably possible, but here it is pretty natural to just have the gamma in it and fill the memory with this gamma correction table right out of Python, put it into memory, and gamma compensate. So what is gamma compensation to? That's the important question here. Our eyes don't see brightness linearly. It is a nonlinear curve. So that is essentially to maximize our dynamic range, how we see. So at the lower brightness values, we see very small differences between low brightness values, but the higher the brightness, the less difference we see. So you have this exponential curve that you want to apply, where you make very small steps in brightness when it is dark, and then start making bigger steps in brightness so that it seems for us linear to our eye. This is why you have gamma correction in your computer monitors in games, and you have to set gamma correction and whatnot. This is exactly addressing that issue, how our eye sees in a nonlinear fashion. So we have that here, and it's compensated. And so the PDM values are not being incremented linearly, which would be making it like go from very dark and then stay for very long time bright. So that's the effect that you get when you have just linear increment. So you have dark, brighter, 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 very bright for a very long time. You don't see any difference, and then it goes down and is for a very short period of time in the dark period. You don't see much difference. It's basically all clumped together in the bright section. With gamma correction, you inverse that so that it is staying the same amount in every steps, and you see this very nicely. Okay, so if I just program this, there we go. There we go. So now, if you look at these LEDs here, up, there. So they are fading. So what you see here is the green LED is not as bright as the red LED, just by how it is. But you see how they are actually breathing quite nicely. And it's not staying in the bright period for very long. It just keeps going, and you keep seeing it going brighter and darker at all times. And the green LED is the inverse of that, which is pretty nice. So I think that's a pretty cool demo of PDM. Also, it's like, even with my eyes, if I try to shake it to see the PWM, I can't. It's really fast. It's 12 megahertz clock rate that it's driving it. So it is really high frequency. So you will not see it fading or blinking in the camera or anything. So yeah, now let's try out simulation. So we have this this process, which essentially takes sets the PDM in to a value between 0 and 256 and yields for a few cycles. So it basically sets a value, waits 1, 2, 3, 4 clock cycles, and sets a new value 1, 2, 3, 4 cycles, and goes from 0 to 256, and then generates a GTK wave or VCD files for a simulation. So let's run that. And all I need to do is just call it, what happened? Oh, S. And it's already done. There we go. And it's already here. So this is the simulation. So you see, we have the PDM in, which is being set to 0, and then ran for 1, 2, so 1, 2, 3, and then set to a new value, and so on and so forth. So you see how the PDM starts with being off most of the time until it increases, then it is blinking at higher and higher frequency. So you see the density of those pulses is increasing. I think it would have to run for a much longer time and let the cycles run so that you see what the value is. So if we, for example, say not 50%, but like let's set it to 64 and just constantly to 64. Let's send it to background and rerun it. And then, what was it? Control refresh, file reload, Shift Control R, Shift Control R. There we go. Yeah, so there we go. I can even add the clock here for reference. So these are the clock cycles, you see, and it runs one clock cycle on and then 1, 2, 3, 4 off. One on, so 1 in 1, 2, 3, 4. So 1 on and 3 off, and so on. So this is the PDM for you, where the ratio of the on and off is evenly distributed over the frequency, which is pretty cool. Okay, so that is simulation for you also in directly in this code, and we could actually have a longer yield set here with also another for loop. So yeah, anyways, I think unfortunately we ran out of time so that I could show you more and maybe even implement something, but we are already beyond the 2-hour mark, right? Because it's 3:30, so we are definitely longer than we should have run. I usually try to keep these to 2 hours. Maybe next time we can implement something, but I hope this was somewhat useful for you. One more thing we can do is actually get rid of this clock here and then remove this clock here. So clean this up. So let's keep cleaning this up here. What is it complaining about here? Assigned but never used. So we have PDM outs that we have, but we don't never use. Interesting. So that's that. And what's going on here with the pins? Yeah, I don't know what. It's probably the indentation is not. It's not happy with the indentation. Anyways, details that I will fix later. But yeah, I hope this was useful. You learned something. I rehashed my nMigen or reiterated the nMigen for myself. I will definitely continue working on this. My goal is to essentially get to a point where we can have a RISC-V microcontroller or a core running with some designed hardware to drive these LEDs here that you see here on the table. To drive these are APA 102s, and have a block to drive these, and then be able to essentially run Twang on this, maybe even on the Icebreaker BitC. So there's a lot of stuff to do in here. That would be quite a lot of fun. Hopefully fairly simple to follow along. And so the problem with LiteX is that LiteX is running on nMigen. I want to use nMigen, and the way, so there is a compatibility layer so that you can run Migen modules inside nMigen, but not vice versa. So because LiteX is all written in Migen, and it is not a priority for the creators of LiteX to move forward to nMigen, because they have bigger fish to fry, they have other priorities, which is totally understandable and fine. I can't use LiteX for it. What I will be doing is probably creating my own. They did mention that they will do that eventually, maybe if they feel like it and there is time. I don't know, maybe this changed and the priorities improved, but that was the last thing I heard, which is, again, no criticism here whatsoever. I completely understand the reasoning here. This is not what I want to put in my effort into. I want to put my effort into nMigen and learn that, and not like pollute my capabilities with an older framework that we will be, as a community, moving away from anyways eventually. So I am thinking this is my approach here will be more like Luna from Kate, which is its own. Yeah, sure, but no, I'm not doing that. I want to really plunge in and use nMigen to its full potential. I rather create a really small. So LiteX is great if you want to run a Linux and a really complex, like, bootable thing with RAM and training of buses and whatnot. It's really great at that. It has all the DDR3 bus training and other things. But for this microcontroller thing, most of what LiteX brings to the table, I don't need. What I was planning to do is use nMigen SOC and build my own really tiny framework that uses Minerva probably, or whichever. It can be some other. It's like for most cases where you need a soft core, LiteX is an overkill. Unless you are really shooting for the stars for some massive machine. And I don't need that. And I don't think this is I want something that is simple. LiteX really was overwhelming with its complexity to try to learn to do things with it. So I will be trying to build something smaller that just has a RISC-V core, maybe even a Verilog one imported, but something like that, and then have just nMigen modules that do other things like SPI. I don't need maybe I2C, we will see, but mainly have that as a core and keep it simple. Probably move some of the documentation tools that Zobs developed for LiteX and bring them into the thing that I'm building and try to do that. So that's my approach. It's probably quite time consuming, but I don't really want to. I think porting LiteX to nMigen is too big of a project to justify for what I need to do, because that would be the alternative. Just take LiteX and port it to nMigen myself if I need it. But I don't feel like this is the right allocation of my time. I try to... yes, there is. There is an nMigen SOC. So let me show you really quick. And there's more than just that. So there's nMigen SOC. So there's already that. So we can use that, and we will be using that. And I think there is also, yesterday commits. Wow, there's a lot of stuff happening here. Another thing, I think it is, how is it called? The name eludes me. Lambda SOC, yes, I think that's the other thing. I think so. There was a thing, Lambda concept. There's from Lambda concept also a Lambda SOC or something. It might be the Minerva. I think is also from Lambda, but there's some more stuff where you can actually build a. Yeah, there we go. Perfect. Thank you so much. Yeah, there we go. So there is also Lambda SOC. So yeah, I think I will be looking at both of these things and trying to get them to run, understand what they do, what they don't do, and see what I need to add to make it workable for my application, to have a small RISC-V microcontroller or core, and a bunch of other stuff. Yeah, so there's I'm pretty sure this also exists here. Yeah, nMigen STDIO. It's like, always be careful that you are on the correct Orga Ratboy. So yeah, yes, that's the correct one. Yeah, so there's SPI UART I2C already there. Great. So we have pretty much all the different tools. Oh no, it's only serial at the moment. Wow. Okay. Well, we need to write some modules then, right? That's perfect. It's like, why having everything just served ready to eat when we can actually make our own food? Won't it be wonderful? So yeah, I am very excited. I think there's a lot of stuff to be done. And I think we can do it in fully in nMigen, or even if we need a module here and there that is Migen, we can integrate it into here. We don't need to do it in LiteX in this big machine. We can do it in smaller chunks and learn stuff doing that. So I'm excited to look into this. Yeah. So yeah, it's all work in progress. It's we all are part of this community. If we want certain things that don't exist, we have to write them. That's not a problem. Just put the effort in, and then it will be for everyone. That's the beauty of open source. We can share the load on everyone in the community and create things. So I am trying to do my part of sharing some info and love and how to do things and how to use them just a little bit. And hopefully that will inspire you to maybe contribute some stuff to the effort. And yeah, otherwise, let me think. Is there anything else that we should talk about? Yeah, I think we should talk about the plans for next. So definitely I will try to do another stream on Tuesday. So there will be one really quickly. We might do a short stream to put together the Lego satellite from just a chill out stream, maybe on the weekend or something. We will see. I will probably last moment announce it so that we can do that. I really want to assemble the icebreaker Bitsies. So either we do that on the next stream on Tuesday, but there is also a chance that I am so impatient that I really want to get it done quicker than this. So we might do it also as an extra stream to just assemble these. Yeah, this will be a very interesting bring up. I'm really looking forward to having those, and I'm sure Jordi will love to have some to try them out because he designed them. So this will be very cool. Otherwise, as always, check the Discord, and thank you very much for the subscriptions here on Patreon, on Twitch. So thank you so much for that, and the bits and everything. The support really matters and makes these streams possible. I want to thank everyone who is supporting me on Patreon. So check out Patreon under this video. Thank you so much for all the supporters, and as always, a shout out goes to Sid Price, which started supporting recently. Thank you so much. Then Aki Van Ness, Jamin, Brennan Ashton, Ben Venick, Drew Fustini, Edward Borden, Go Jimmy Pie, Jeff Wang, Jordi Parky Rodriguez, Kelly, Matis Schmiedle, Miha Benovets, Sean C. and Tom Keddy. Thank you so much, everyone who supports the streams on Patreon. I really appreciate that. Yeah, if you have any questions, ask me on Discord in the streaming channel or whatever the topic is that will be applicable to this. If you want to join the community, please join. Everyone is very much welcome. We try to make it a nice and pleasant place to hang out and talk talk shop and let's build some awesome hardware with open source tools. That's the goal. So yeah, as always, thank you for watching, and see you next time. Bye.